Just a last little note, the tape cut off before I could get down here. If we have an AC source, we'll often represent it by a circle with kind of an alternating current in here. We aren't studying AC circuits, but I'll just try to familiarize you with that notation a little bit. Okay, here we have a three-dimensional sketch. We have a charge moving with a magnetic field aimed this way. Now this magnetic field we think is aimed in the direction of this axis here coming out of the paper, and the motion of the charge is in the direction of this axis. Okay, so we have a velocity that's perpendicular to the magnetic field, so that the force on the charge, well, the general expression for the force on a charge moving in a magnetic field is QVB times the sine of theta, where theta is the angle between the magnetic field and the direction of motion of the charge. And that force is going to be perpendicular to both the velocity and the magnetic field, and by the right-hand rule. Okay, so we think of crossing the velocity. In this case, I can't really turn my hand that way. And maybe if I step in front of the camera here. Okay, the charge is this direction. The motion is in this direction. The magnetic field is in this direction, so I've got to turn my hand around like this, and the force will be downward. Hopefully you're able to see that. So they have a downward force in this case. That's the effect of a magnetic field on a moving charge. And of course, we extend that to a lot of charges moving in a wire. Instead of Q times V, the product of charge and velocity, we do current times length. And it turns out, we've seen the argument that current times length is equivalent to charge times velocity. And we get the force as ILB or IL cross B if we have an angle other than 90 degrees between the magnetic field and the current. Now if we have a loop of wire with a current I passing through the loop, in the presence of a magnetic field, the B field directed in this direction, then what kind of forces do we get? Well, I is in this direction, B is in this direction, so that I cross B, okay, I is this way, B is this way, I cross B is this way, into the paper, depicted by this red force vector here. On this side, I is upward, B is in this direction, so that the field will be coming out at you like this. And these two forces, of course, give us a tendency to rotate, or a rotational torque of this loop. We have zero force in the portions of the wire that are parallel to the magnetic field. That's because of this sine theta. When the current is parallel to the field, then the angle is 0, and the sine of 0 is 0, so there's no force. So that's the net result here.